All right, this is number 4 from section 4.3. Let's take a look. I thought this one was slightly interesting. It says find a basis for the set of vectors in R3 in the plane x minus 3y plus 5z equals 0. Okay, in other words, this is a plane inside R3. Okay, and it's a subspace, so we should be able to find a basis for it. So how do you find a basis for all the vectors in this plane? Well, one way to do it is just to observe that if you solve for x, you get 3y minus 5z. So we could characterize all of the vectors in that plane just as a 3 by 1 column vector and just replace the x with a 3y minus 5z. And we'll leave the y and the z as arbitrary. And then we'll do a trick that we've been doing many times. I can write that as a linear combination of two vectors, 3, 1, 0 times y plus negative 5, 0, 1 times z. All right, so certainly all linear combinations of these two vectors will span the space, the subspace. So the only thing really left to check is that these are linearly independent. And I think it's pretty easy to show that they are, but we probably should show it. So they certainly span the space of the plane, but we also want to show that they're linearly independent. So let's assume that this is true. Remember, that's how we always check linear independence. And let's try to show that if that's true, x1 and x2 both have to be 0. So the augmented matrix for that system is this. Okay. All right, so what should we do next? Well, I guess I could divide the whole first row by, in fact, I'm just going to use a calculator to put this thing in reduced echelon form. Let me do that. Save a little time. So the calculator tells me this, that the matrix is row equivalent to this matrix in reduced echelon form. Okay. But notice that implies that x1 is equal to 0 and x2 is equal to 0. So that proves they are linearly independent vectors. So that is a basis for the set of vectors in the plane. And I'm talking about this vector and this vector.